Okay, welcome everyone to Guided Study Group week 13 of my 141. So I hope everyone is so far has been doing enough practice to get familiar with the power series and so on, and how to find its representation. So this week we're gonna get a touch on 11.10 and 11.10 and 11.11, which is Taylor and Maclaurin series. So a little bit more about the Taylor series, which is kind of like giving us more feeling about the coefficient, which last week we just assumed that the coefficient of all the terms in the series is going to be 1. Cn is 1. But this week we're actually going to come to find Cn and how to find it in Taylor series and Maclaurin series. Then we also have the Taylor's inequality, which is kind of like the application of Taylor series. It allows us to do some approximation of some maybe function like sine x or cosine x at some value of x, and also it allows us to estimate what is the area of that, what is the error of that estimation. So let's get started. We have 11.10 and 11.11, Taylor and Maclaurin series. So the theory is not much, but I would say for this section it's a lot of intensive practice. So now we have a theorem saying if you have a power series representation at A, then the coefficient Cn is given by Cn equal the nth derivative of f at A, nth derivative of f at A. So basically you find the nth derivative of f and then you plug A in over n factorial. Now for the Taylor series, we should have a general function, that general power series at center at A. Then your fx is going to be the series from n equals 0 to infinity, the nth derivative of f at A divided by n factorial multiply x minus a to the nth. If you have Maclaurin series is kind of like the special case of Taylor series where you have the function center at 0, so a equals 0. Then you just have the series following what you have, following like kind of like similar to the above series. Now you have the application of the Taylor's inequality. So when you use, say, the Tn of x to estimate or approximate f of x, then this is the error related to that. So find a Tn of x, say T fourth of x is really easy, which is just using these two functions that I just mentioned. But this is how you're going to estimate the error. So you're going to have the Rn of Rnx, which is going to be the actual value of fx minus Tn of x. So this one, the error, which is, I would say this one is the error, it is going to be smaller than or equal big M divided by n plus 1 factorial, x minus a to the n plus 1, for x minus a smaller than or equal to d. So basically it was saying the error is smaller than this expression, would m be the maximum value of f to the n plus 1x. So m be the maximum value of the n plus 1 derivative of f on that interval. So for on that x minus a smaller than d, or on the kind of like interval of convergence. Then you have x minus a to the n plus 1. This one is also be the max value of this m, actually this x minus a in the absolute value, it have to be max of absolute value of x minus a on the interval of convergence. Or actually it should be, I will put this way, it would be best to be put in the way of m, the maximum value of the n plus 1 derivative, n plus 1 factorial multiply d to the n plus 1. Yeah, with d is the maximum value of x minus a on that interval, on the interval of convergence. You're going to see this in the example very clearly. We also have some problem that you might be asked is find the sum of a series. So you have to put it in the form of maybe like you given this series and then you go way backward, you written it in this way. That's how you're going to find the sum. Or you can be asked to estimate the maximum error when using the Taylor polynomial for the nth derivative degree to approximate any function of fx. And then number 3 is just like use the Taylor polynomial to approximate it. Some important Maclaurin series and their radial convergence. So this one is I kind of like put it all together from your lecture notes and also book notes. It's basically saying you have these function 1 over 1 minus x, e to the x, sine x, cosine x, inverse tangent of x, and these are gonna be the Maclaurin representation of them. So I think it's a very good note to keep because it's gonna save you a lot of time in I think maybe the exam or just your practice, so that you don't have to look through all the notes, like I think 30 something pages. So I think it's very helpful to have these hand, and also from what we have last week, I think last week we have 1 over 1 minus x, 1 over 1 plus x, ln of x, ln of 1 plus x, and then I think 1 over 1 minus plus or minus x squared as well. So yeah, I think that's what we have last week. I think this one is also plus or minus. Yeah. So I think that's what we have last week. I think it's also helpful if you want to keep a note of all of that. I personally keep the note of all of these just for the purpose of final review because I think it saved me a lot of time just instead of going through all the lecture notes again just to keep track of this. So that's all of the theory that we have today. So let's start with the example. Let me see how many examples I have. 1, 2, 3, 4. Sure. So let's do example 1. Express the indefinite integral as a Maclaurin series. So this one is going to be, give me a second. So we have cosine of x minus 1 over x. So to find the Maclaurin series of this, we have to apply with dx. Find a Maclaurin series of this. So the first one is to Maclaurin series of this is cosine x we have from the table that we have here. Table here. So you're gonna have the series from n equal to 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. So series from n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial minus 1 divided by x dx. Now what does this thing equal? If you kind of like expand a few terms, you're gonna see that it's going to be it's also have the exponent here. So 1 minus x squared over 2 factorial plus x fourth over 4 factorial minus x 8 over 8 factorial until you have the end thing, and then you have minus 1 over x dx. So what does it give you? Basically the 1 cancel out. So basically the first term of n equals 0 in this series disappears. So you only have from infinity n equal 1, negative 1 to the n, x to the 2n divided by 2n factorial. So the only thing changed is your starting n this time over x dx. So now let's do some algebra before you take the derivative. No, take the integral of this. X to the 2n minus 1 because you divided by that 2n factorial dx. Now when you take integral, so what end up having is that you keep your n, as I said last week, and then you have negative 1 over n is just a constant divided by 2n factorial, also a constant. Then you have x 2n divided by 2n again. Is it? Let me have a look at that again. So we have the series, and then when we take derivative of that, so basically it's just, yeah, I think it's the correct one, right? So that is, and then you have a plus c, you don't mind. So that's the Maclaurin series of that integral. So basically you just first you plug in the Maclaurin series of cosine x, you do some algebra to kind of like simplify everything until this step, and then you just take integral normally, like what you usually do. So that's our example 1. So the tricky part over here is just well, you look at that integral, and the first thing to do is that knowing the fact that you're going to plug the Maclaurin series of cosine x in. And I think it's pretty helpful because honestly, when you look at these questions, if you don't know the Maclaurin series of cosine x, it kind of takes a while for you to figure out exactly what you have to do. But yeah, that's the first step. So now let's go to example 2. Find the sum of the series. So now this one, I would say, as I said, like the way to find the sum kind of problem is that you have to rewrite it maybe in the form of the function that you want, and then just plug in to find it. And then you have 4 to the 2n plus 1. So now let's look at the table because it does remind me of something. So you have 2n plus 1, negative 1 to the n, and then x to the 2n plus 1. So this one is going to give you the Maclaurin series of sine x, but there's something you need to rewrite first. So you have negative 1 to the n over 2n factorial. And then you're going to have pi over 4 to the 2n plus 1. So I just remind you from that table, you have the series from n equals 0 to infinity, negative 1 to the n over 2n plus 1 factorial with x to the 2n plus 1. This is going to be the Maclaurin series of sine x. So instead of x here, you have pi over 4. So basically this one is equal to sine of pi over 4 because this is the Maclaurin series representation of sine. So this one, you basically just find what is sine of pi over 4, which is going to be square root of 2 over 2. So that's what we have. So the step in find the sum of the series is always rewrite it. However, you have to familiarize yourself with a lot of the series that we have already done so far, or like know how to derive those series. That is going to come from a very good habit of documentation, and also do a lot of practice if you see some series that you have never done before. But you can maybe like do some algebra in your head that you can derive it from integral or derivative, as what we learned last week. Now we go to the last example, example 3. Consider the function f(x) equals x squared ln of x on an interval of half to 3 half. Find the Taylor polynomial for the third degree C3x at a equals 1. Now, so basically you have fx be the Taylor series, so n equals 0 to infinity, of this. And so this one is going to be this one is Cn, which the Cn is now become f to the n of 1 n factorial x minus 1 to the n, and this one is equal to x squared ln of x. So now we need to find t this is t and x. We have to find t free x. First of all, I would say you need x here, f of, so you have f prime of x. You have, so n starting from 0, so you need fx as well. So you need f of 1, f prime, f of x, and then you have f of 1, f, sorry, it's a little bit. So you have f prime of x, f double prime of x, f triple prime of x. And then you have f1 prime, f2 prime, and f double triple prime. Now, f of x is x squared ln of x, so when you put in 1, it's going to be 0, because ln of 1 is 0. Then you have f prime of x, so when you take derivative of this thing, say this is where it comes to be complicated. So it's going to be 2x ln of x plus x squared 1 over x, which is going to be 2x ln of x plus x. So you have f prime of 1 be, this one is 0, and then you're just going to have 1. Then you have derivative again, so you're going to have 2 ln of x plus 2x ln 2x multiply 1 over x, so it's just going to be 2 plus 1. So this one is 2 ln of x plus 3, which is give us the second derivative at 1 is 3. And then finally you have 2 over x. Then you have triple prime. So third derivative of f at 1 is going to be 2. Now you have that. So now you're going to have t 3x is going to be, so the first one, the coefficient is 0, so you don't plug it in. Now it's 0 plus, second one is 1, x minus 1 to the 1 factorial, plus, now n equal 2, so you have 3 x minus 1 square over 2 factorial, and then finally you plus, the third number is, third coefficient is 2, x minus 1 third divided by 3 factorial. Now, if you do some algebra to simplify it, yeah, so you're gonna have x minus 1 plus 3 over 2 x minus 1 square plus 2 over 6, so it's gonna be 1 over 3 x minus 1 cube. So it's not too complicated. You have the step that you just need to follow, and the coefficient is just finding the derivative. Now, the next question is use that Taylor's inequality to estimate the accuracy of the approximation that we just did before. So now, you're going to have n equal to 3 earlier because you used t3 of x to estimate. So you're going to have to find the fourth derivative of x to find the error. So the formula for the error is Rn of x. Here you have n equal to 3. So R3 of x equal, or smaller than or equal, max of f4 of x on that interval, n plus 1 factorial, which is 4 factorial, x minus 1 to the fourth, and this also have to be max. This is absolute value. So this here, you're going to have the fourth derivative is negative 2 over x squared because the third derivative is 2 over x. Then you have max of f4 x on half to 3 half. Let me see the interval that we're given. Yeah, is equal to. So when you plug in different values, so just looking at it here, max of this. So max of the absolute value as well. So max of the fourth. So here basically when you put in the absolute value is just 2 over x squared. And if you want this fraction to be maximum, if you want the absolute value of the fourth derivative to be maximum, so 2 over x squared maximum, then you need x squared to be minimum. X have to be minimum as well. So basically it's equal to 2 over half square, because half is the smallest here. Is equal to 8 at x equal to half. So here you have the value to put in. So this one basically is smaller than or equal to 8 over 4 factorial. Now you also have, what is x minus 1? The absolute value that is maximum. So maximum of absolute value of x minus 1 on this interval. When you look at it, you have 1 half and then 3 half. So basically this is a symmetric interval. So it has to be at either of the two ends to be maximum of x minus 1. So basically this thing, the inside maximum is just half, because the distance is equal from the two ends, and it's also the maximum distance as well from 1. So it's half. Therefore you have this arrow is equal, I would say 8 over 4.32, and you have 1 over 16. So you have 8. It will eliminate these, so it's gonna be 1 over 48. And I don't have an actual decimal number, but that is our final answer for the arrow. So this is the maximum error if you use a third degree Taylor polynomial to estimate our function fx. So it's not hard, it's just the fact that you have to take care of different stuff like the fourth derivative and then the x minus 1 maximum, and so, but you need just do a lot of practice and get used to it. So if you don't have any more questions, that's all I have for today. Some of the final notes for this part, because I think next week we're going to touch on polar coordinates and parametric curve. So it means that from now on, from next week to the end of the semester, I think like in 2 more weeks or 3 more weeks, we wouldn't touch on Taylor or power series anymore. So you guys have to do a lot of review on yourself for the final exam, because we wouldn't have another sections for that. So what I would recommend doing is review the exercise of the power series before, document all of the series that you've done so far, as I said, like 1 over 1 minus x or 1 over 1 plus x and ln and all of that stuff. Know the general formula of the Maclaurin series of specific function. So just like sine x, cosine x, inverse tangent of x, or anything in the table that I show you just in the review today. Know the general Taylor series of any function. So this is the one that we set to say Cn is m fn a over n factorial. And so the series, Taylor series, is just going to be this coefficient and then x minus a to the n. Do all the problems in the book that ask you to find the sum of a series or express the integral as an infinite series or use the n degree Taylor polynomial. So basically everything that we did in this review so far, like things are similar to the 3 examples, because I think those are the very good practice for the final exam, and also I think one of the main focus for power series. So it means that if you want to show the fact that you master power series or understand it, you should be able to do these 3 of exercise, and some even more, but these are the 3 basic ones. So that is final note. And then I have some practice problem here, which you guys can feel free to try it when you guys at home and want to do some more practice. So that's all I have for today. So have a great weekend, guys, and we're gonna start on polar coordinates and parametric curve next week. I'll end the meeting here. Bye.